You're listening to the first installment of CreatureCast, a podcast about animals brought to you by some of the people who study them. This is Sophia Tintori from Casey Dunn's lab at Brown University in Providence, Rhode Island. About a month ago, I was lucky enough to find myself 200 miles off the coast of California on a boat with 9 scientists. One night after dinner, when some folks went back to the lab that was inside the ship, I went and took a walk out onto the back deck. And when I got out there, the 2 squid scientists were standing by the edge of the boat, and they had a line in the water, and there was this pale blue squid that was lying on the deck next to them. The squid was moving slowly, and there was something about the animal's smooth, muscular skin that made me really just want to touch it. But as soon as I put a finger down, these colors went shooting across the animal's skin. And if I dragged my finger gently across its body, it would leave this white trail behind. And whenever the squid moved, these pulses of blue and brown would go swirling across the body in pretty alarming flashes. Luckily, one of the scientists who was standing out there studies particularly the crazy things that squids can do with light and with color, and so I got to ask her some questions about what was going on. Her name is Allison Sweeney.
I'm Allison Sweeney.
And the squid is called Loligo.
My sort of workhorse squid was Loligo opalescens, which is the restaurant squid, the one that you eat when you order calamari most times.
Bada bing, calamari.
Okay, I've heard of chromatophores. Those are the colored cells that the squid can make bigger or smaller. So, for example, by making the darker brown cells large and the lighter yellow cells small in choice areas, they can create patterns of brightness and darkness across the body. Is this what I was seeing on the boat, or were there other things going on here as well?
So, it turns out that all squids and octopuses pretty much have a layer of iridescence underlying their chromatophores. So the chromatophore cells, the ones that expand and contract and make different patterns on the bodies of squids, are pretty famous. And what's less famous is kind of the iridescent layer underlying that. But it turns out that the two working together are probably key to their ability to camouflage themselves.
So squids have iridescence, that same shiny, metallic-looking, reflective quality as butterflies or the green shells of beetles. But I've never seen colors pulse across the wings of a butterfly the way they do on a squid. So how is this the same phenomenon?
So in iridescent butterflies and iridescent lizards, they use kind of these immobile, hard, essentially dead structures in the epithelium or on the wing scales to achieve their iridescent effects. But in squids, because it's inside cells, inside the skin, they can actively change and modulate and rearrange these self-assembling proteins to make pretty much any optical device they care to make in their skin, which is pretty amazing.
As I was kneeling next to this squid and watching the colors pulse across it, coming in waves off of any little motion the animal made, which felt a lot like watching an iTunes visualizer of its thoughts or something like that. The squid was doing at least a couple of really unbelievable things at once. Not only was it opening and closing its chromatophores, the cells that are filled with an already made pigment that simply get turned on or turned off, but it was also actively fabricating entirely new colors from scratch. And it was synchronizing the two things with each other.
So Loligo opalescens, the restaurant squid, it has these crazy iridescent cells that it can completely disassemble the iridescent structures and then reassemble the iridescent structures, and not only reassemble them but make them reflect any wavelength in the visible range, and then they can do this in a controlled fashion over the whole surface of the body. And they do that with these proteins called reflectins.
Each iridescent cell has lots of proteins in it called reflectins. And each of these proteins has a really huge electrical charge. So just like if you're trying to force together the similar ends of two magnets, all of these similarly positively charged proteins are pushing it away from each other, keeping their distance in a relatively evenly spaced way. When the squid wants to, it can add these little extra pieces to the positively charged proteins, and the little pieces are negatively charged, and so they end up neutralizing the protein a little bit. And when they're neutralized, they don't push against each other as much, and they can pack in closer. The closer the proteins can stack against each other, the shorter the wavelength of light is that's reflected off of them, changing the color that comes off the squid's skin.
So reds are longer wavelengths and blues are shorter wavelengths, and so the tighter you make your reflective stack, the bluer or more ultraviolet even the wavelength back out is.
This is pretty amazing because usually when we think about color on a molecular level, it's the size and the shape of the molecule that determines what color is going to bounce off of it. For example, this is the way that it works in chromatophores. But in iridescent cells, the color is actually determined by how much space is in between the molecules. And squids have figured out how to make color in both ways. Okay, this seems like a pretty important thing to them. Why are squids even doing this in the first place?
We think that a while ago these food squid are some of the only squid that live like really shallow in the open ocean. And so there's a phenomenon called wave lensing, which you've seen if you've ever been in a swimming pool, just that process of bright bands of light moving across the bottom of the pool because there are waves having a lensing effect moving across the top. And so in order to be camouflaged in this vast open ocean right at the surface, if the squids can move reflections across their body at the same frequency as the wave lensing at the surface, this probably affords them a good degree of invisibility from the top and the sides.
So how do they know what pattern to make to match what's going on around them?
We don't really know. Is it the eye? Is it looking at the scene and then, with its eyeballs and then making a decision that way about what pattern to make? Or are there photoreceptors in the skin? Is it some actual direct effect of light hitting the body of the animal? That'll be another part of the experiment, is trying to glue little goggles on squid eyes and seeing if that makes a difference.
Well, thanks so much to Dr. Allison Sweeney.
Thank you.
Thank you.
Yeah.
It's fun.
As well as to Danny DeMartini and the Morse Lab at UC Santa Barbara for figuring out a lot of the stuff that Dr. Sweeney just explained. And I can't wait to see what the blindfolded squid do. CreatureCast is produced with support from the National Science Foundation. I'd also like to thank Lucky Dragons for their music, as well as Rachel Blatt and Ike Sriskandaraja for their guidance in these young and blossoming days of the CreatureCast. Visit us at creaturecast.org to learn more fun stuff about the unexpected world of animals. From Providence, Rhode Island, this is Sophia Tintori. Thanks for listening.